So thank you for the introduction. I'm going to present to you joint work with Edward Eaton, Alex Parent, and Nicolas Andrier. So let me just recall the context. You all know that we're here to study public key cryptography and especially find post-quantum solutions, and this morning's session is dedicated to code-based crypto. So our main goal here is to achieve a crypto system with relatively short keys, shorter than the Makelis-Gopa original solution. And the solution that we are going to study here is using the idea of using cyclic structure, as Marco Baldi said this morning. And so there was this MDPC proposal, same as LDPCs but with moderate density, so density of the vectors in square root of the length. And so we're going to study here the quasi-cyclic version. So let me recall the scheme. You can see it either as cyclic, circular matrices or polynomials over divided by x to the k minus 1. So Alice chooses two polynomial h0, h1, and sparse polynomials, and sends her public key the quotient of h1 by h0 to Bob. And Bob chooses two random error vectors, sparse also. You can see that here the weight of the sum of the vectors is t, so it's square root of the length, approximately, and sends e0 plus e1 times q. Alice can multiply this by h0, she gets e0 h0 plus e1 h1, and using this and the knowledge of the fact that the knowledge of h0 h1 and the fact that all of this is sparse, she manages to decode this and recover e0 e1. At the end they will share the secret e0 e1, and what's nice here is that there is an efficient decoding algorithm. So decoding algorithm is basically syndrome decoding. Okay, you have access to h0, h1, which are the first rows of the circulant matrices, circulant blocks of the matrix, and you have the syndrome, you want to recover e0, e1 sparse enough. And so you've seen this algorithm because it was discussed by Marco, and all you need to know about this algorithm to understand what I'm going to say is first that it's an iterative algorithm. Okay, there is a while loop, and so the number of iterations may vary from one instant to another. That this algorithm fails with a small probability that I will refer to as the DFR, decoding failure rate. And also, and Marco talked about this, that there are some choices of thresholds to be made, and this has influence on the algorithm. So at AsiaCrypt in 2016, Guo, Johansen and Stankowski proposed an attack exploiting the properties of this algorithm. The main observation is the following. When you have two non-zero bits, so two 1 bits appearing at the same distance delta, both in the key h and in the error vector, then a decoding failure in the algorithm is a bit less likely to occur than on the average case. So here, what do I mean by this? Well, for the sake of simplicity, I represented this with only one block. Usually it's two blocks, but it's exactly the same that is happening. Here, for example, you see in the error vector, you have two bits at distance ones, okay, they are next to the other, and this happens also in h0, so h, the first line of the circulant matrix. And so in such a case, this happens twice here, decoding failure is a bit less likely to occur. And by observing the failure rate for different error patterns, they say that they can recover the key. So they define the notion of distance spectrum. Distance spectrum is just, let me show you on this example, it's the distances between two 1 bits in a vector. So here, for example, for instance, those 2 bits are at distance 1, in fact, because they are counted cyclically. Those 2 are at distance 3, and those 2, there are 5 zeros in the middle, but if you count cyclically, it's at distance 4. So the spectrum of this age would be 1, 3, 4. So the main general attack pattern for such a scheme would be measure in any way you want the value of the spectrum of H and then reconstruct H from the spectrum. I'm not going to discuss the reconstruction phase because this is an algorithmic problem that was already discussed in the original GJS paper. So here's what they do. Imagine that you have somehow access to a device that is Alice's decoder, so it contains Alice's private key, and Eve can send random ciphertext to the device. So she doesn't choose the value of E, but she knows the value of E. And she sends random ciphertext, and all she can know is whether or not the decoding failed or succeeded. And by exploiting this, with this information that if there is a same distance in E, in the spectrum of E and in the spectrum of H, the decoding fails a bit less on average, they manage to recover the full spectrum of H with sending random error patterns. Now, why does it behave so? Well, most decoders, actually all QC-MDPC decoders, start by computing the syndrome, okay? It's the natural thing to do. So, how does this syndrome computation work? Well, the syndrome is just each bit of the syndrome, it's the inner product of the row of the matrix and the error. So, for example, the first bit of the syndrome, 0, is just the inner product of E and the first row of the matrix. So here there are always 0 or 1 or 1 or 0, so the total is 0. Next you have 1 and 1, so the total will be 1. Same thing here, 1 and 1, the rest is 0, 1, etc. Here you have 0, 0, and here what happens is that you have 1, 1 and 1, 1, but they cancel out because you're doing the inner product in F2. So you see here that this happens exactly when you have two ones at the same distance, both in the error vector and in the key. So what would be the average syndrome weight? Well, if you forget about the quasi-cyclic structure, just think of a random MDPC matrix. Okay, all the rows are independent, they just have the same weight. So the weight of the syndrome is just k, that's the size of the syndrome, times the probability for each bit, for each inner product to be 1, okay, which we can compute easily with binomials. Now, suppose that we are in a case, as we've seen, with a distance that is the same in the first row of the matrix and the error. So here we have 1, 1 and 1, 1. So when you shift the first row, L times L is the multiplicity, the number of times that this distance repeats. L times you will have 1, 1 and something else. Then just before or after that, in the shift, you'll have 1, 0 plus something else, 0, 1 plus something else, and the remaining cases is 0, 0 and something else. So if you know now that your error pattern is 1, 1 and something under something remaining, you can give a more accurate formula for the average syndrome weight. Okay, this formula depends on the multiplicity L, which was 2 just in the example. In fact, it depends linearly in the multiplicity. And this explains, if you compute this approximation, the fact that you have a slightly lower syndrome weight in the case of a common distance in the spectrum of E and the spectrum of H. Why is that so? Well, just as we've seen, okay, when we have 1, 1 and 1, 1 at the same position, this cancels out to 0 in the inner product, and of course, this lowers the syndrome weight. So how to turn this into an attack? Well, just as in the original GJS attack, imagine now that you have physical access to the decoder, and you can not only spot whether or not the decoding failed, but you can measure somehow physically the weight of the syndrome that is being computed. So what you get in return is sigma, that denotes the weight of the syndrome. So you send different ciphertext, random ciphertext, and you just observe the weight of the syndrome. Here's what happens. Here I plotted for different distances that I know that for all distances, all possible distances, the average weight of the syndrome. And when you increase the number of samples, here's what you get. You get those clusters, just as in the GJS attacks, that correspond. First one, the black row, is the distances that don't appear in the spectrum of H. Okay? So that would be actually the average case. Then in red are the distances that appear once in the spectrum of H. So this in those cases, you see that the average syndrome weight is a bit lower. In blue, those that happen twice, and in green, some appear 3 times. So from this, you can decide for each distance whether or not it appears in the spectrum of H, and recover H, and you have access to the private key. So here are some numbers just for bike 2. And what's interesting is that it works regardless of the failure rate, because you don't need to wait for the decoding to fail, which happens once every 10 million examples, to get information. And also that any value that would be correlated with this syndrome weight, sigma, could leak some information, just as here. And for instance, I've told you that the decoding algorithm is an iterative algorithm, and the number of iterations of the while loop depends on the syndrome. So it depends on the syndrome weight. So now if we turn this into an attack where we don't watch the syndrome weight, we watch only the number of iterations, which is something that we can sample time probably. So we just send random ciphertext, get access to the number of iterations of the algorithm, plot this, you see exactly the same thing happening. Here you see that the number of iterations is always something between 3 and 4, but it's enough, if you have enough samples, to recover the full spectrum. Here are some examples, some numbers for K or bike 2. So 2 to the 28 sample is not so expensive, right? Of course, the correlation depends on your choice of decoder. These examples were run with with one decoder, but in fact, there are several variants of decoder. For example, there are those called fixed threshold versus variable threshold. I'm sorry, we don't see the title. And on the left you have the fixed thresholds, on the right you have the variable thresholds, and the more important the slope is, the more correlation there is. So here you see that with those variable thresholds choices, you have more correlation. Of course, this is not surprising, because those are choices that are made depending on the syndrome weight, because we want the algorithm to be more, to correct better, to be more tuned. So we make it depend on the syndrome weight, but what we get at the end is that, of course, it's more correlated, so it leaves more information. Also, another interesting choice is your implementation choice, whether you choose in-place or out-of-place decoding, could in fact inverse the sense of the correlation. Here you see that the purple cluster is lower in the first example, in-place decoding, and higher in the out-of-place decoding. Now with our tools, we also can define, compute the values, the average values of those clusters, the black cluster, the red one, and we have formulas for those. And what's interesting from this is especially that we can compute the distance between two clusters. And this relative distance is important for the following reason. What we're doing here, in fact, is just deciding for each distance whether or not it's going to be in the spectrum. And each time that we run a decoding, each time that we send a ciphertext to be decoded, we are performing a test, which is somehow Bernoulli trial, and so we can apply here the statistics results, and especially chain of bound and hypothesis testing, which tells us basically that on average you need 1 over epsilon square Bernoulli trials to make an educated guess. So this gives us a polynomial estimate on the number of samples that one would need to recover the spectrum. This is interesting because you can reverse this and say that, well, I don't want anyone to decode more than that number of ciphertexts on my key, and if you can deduce a bound from those results. Now, how to mitigate all of this? The actual cake bike schemes, you cannot lower the failure rate as much as you want for now. So here was a proposal that's named PARQ. It's a new key encapsulation mechanism that consists into enciphering several independent ciphertexts. Instead of just giving one QC-MDPC encipherment, you take several different ciphertexts, and your key, well, your ciphertext will be the P, C1 to CP different ciphertexts. So when you decode this, when you want to decapsulate, try to decode any of those, and you will consider that the decoding fails only if all of them fail. So of course, for all of them to fail, it's just the probability that all of them fail is the probability that one fails to the power P. So therefore, you can control the DFR, the decoding failure rate. You have the same key sizes as the usual QC-MDPC. Of course, the ciphertext size and the complexity is multiplied by P, but the failure rate is at power P. So for example, if you had 2 to the minus 3 as failure rate, take P equals 12. It's pretty big, but you can deal with it. And you have now a failure rate 2 to the minus 276. And then now you can make a full NCCA to proof in a model including the possibility of a failure of the decoder. So we have performed the theoretical analysis to understand the GJS attack and identify the origin of this attack. We have seen here a generic error pattern that we understand because it's inherent to this quasi-cyclic structure and the inner product of the syndrome, where this information disappears in the inner product, and that now we know that any parameter correlated to this weight of the syndrome could lead to such an attack. We've performed some experimental work with this side channel attack on the syndrome weight and this timing attack on the QC-MDPC codes. And we proposed some countermeasures which include this bound on the allowed queries, for which we can now give an estimate, and a new key encapsulation mechanism. Thank you for your attention.